So we have heard a few workshops and tutorials on deep learning. So today I'm going to talk about how we can use deep learning to accelerate address basic scientific questions in one of the most fundamental problems in biological and in the natural world, which is how the brain works. So so why we are interested in brain research? So we know that brain is by far the most complex piece of organized matter in the universe, and actually it is the least understood human organs. We all know how the basic human organ works, like kidney, heart, etc., and we know very little about how the brain works. And one consequence is when it comes to brain disorders, and there is, for example, in only America, there are currently about 5 million people suffer from Alzheimer's disease, and the cost of education per is like 200 billion per year. And we have a range of other neurological and developmental diseases from brain, and we do not have an effective treatment for almost all of these brain diseases. So the fundamental reason for this is we lack a very basic understanding of how the brain works in health and in disease. So this is one of the most fundamental problems in neuroscience and in biology, and we try to use machine learning, deep learning techniques to help them accelerating their scientific discovery. So when it comes to brain, so the brain is basically a collection of neurons that are connected to each other. For example, the simplest model would be the WMC elegans. So the WMC elegans contains exactly 302 neurons, and it makes about 6 or 7,000 connections between the neurons. And the mouse has roughly around 75 million neurons that make a lot more connections, and human brain is roughly 1,000 times larger in terms of number of neurons, and it makes more connections. So one of the most fundamental research in neuroscience in brain research is we have neurons and connections between neurons. How can we identify the neurons and their connections? So the simplest model we have been working on is C. elegans. Okay, this worm contains 302 neurons, and people have been trying very hard in the 1990s, 1980s, try to figure out what is the shape of each neuron and how these 302 neurons are connected. And this effort took roughly 10 years for people to manually reconstruct the entire connectivity of the 302 neurons. And now people start, and by the way, this is the only organism we have the complete connectivity between each neurons. That is the only organism we have so far. And as we move to the new scientific frontier, we want to address more fundamental questions in higher organisms like mouse and human. And to address this question in human brain is a huge challenge because the size of the brain and the number of neurons and their connectivities. And there is a recent estimate. So if you try to characterize the entire connectivity of human cortex only, and the amount of data you will need will be close to the total amount of information that is recorded globally in all computers today. So this is a huge big data challenge. So just give you an idea of how this process works. So you will usually need to get a brain in order to do reconstruction, and you get a tiny piece of brain because currently we can only, our capability allows us to handle only tiny piece of the brain. Usually, roughly I think about the order of 1,000 of neurons, and then cut the tissue into slices and using electron microscopy to take high resolution images, and based on the images you do reconstruction of each neurons and their connectivity. And so what we'll talk about today is given these images, how to do reconstruction in efficient and accurate ways. And this is one of the major aims of the brain initiative by U.S. government, and this is a huge big data challenge. So just give you a rough idea of how this process works. So given a three-dimensional tissue, so we're cutting the tissue into slices, and each of the tissue slices will be imaged by electron microscopy. We take high-resolution pictures, so we get a set of two-dimensional high-resolution EM images. And given these images, we need to label each of these pixels in the image by the brain tissue that it belongs to. Either it's a membrane or other part of the brain. And then once you do the labeling, so different colors represent a different part of the brain, then you put all these slices together, then you have a three-dimensional reconstruction of the neuron. Here, the different colors represent different neurons, and then you can detect how each neurons are connected based on their exact contact. So here, for example, we have 4 neurons, and we know how these 4 neurons are connected exactly based on their reconstruction. So, and these are the image, three-dimensional EM images. So this is the segmentation, the labeling of each voxel in the image by their tissue structure. And once we have this exact labeling, so we can reconstruct the shape of each individual neurons and how these neurons are connected. So this is just an illustration of how this process. Given this labeling, we can put this in a three-dimensional space, and we can characterize the shape of each neuron, and then based on that, we try to detect how these neurons contact each other, and then we have the connectivity between individual neurons. Okay, so for example, this is the exact connectivity, the shape of one neuron, and this is the shape of another neuron, and based on their contact, we can see these two neurons contact at this particular location. And if we have many neurons, we have many points of contact, and by putting all these together, we essentially get a connectivity matrix between individual neurons. Okay. And here, each row or column represents one neuron. So if you reconstruct the entire human brain, you will have roughly 100 billion rows and 100 billion columns. You can imagine this is a huge matrix to work on. So just give you another example of what are the reconstruction. Here, this is a reconstructed connectivity between roughly 1,000 neurons. So this is a real reconstruction. You can, once you dive into this connectivity, you can see, each neuron can make connections with many other neurons. And even this only like 1,000 neurons, you can imagine their patterns are extremely complex already. So this is the blood vessel. So, and there are some axons dangerous around this blood vessel. So this is just to give you some background. So one of the fundamental questions we try to address is, given these EM images, how to determine the label of each individual pixel on this image. And we have to do this in a three-dimensional space. Okay. And once we have the segmentation map, we can put all these slices together, and we can reconstruct the shape of each neuron, and based on their contact, we can determine the connectivity. So, and this is basically a pipeline of several steps, and the segmentation step is one of the most fundamental steps, because the accuracy of this step really determines the accuracy of downstream steps, like how the neuron, once you have the exact shape of each neuron, then you can determine what is how the neurons contact each other. So this is the problem I will talk about today. So given images, how do we do labeling of each individual pixel? So, and this is basically a very common problem in other areas as well. in computer vision, in natural image processing, and in other areas of biology, like bioimaging informatics. So given some images, what we usually do is compute some features from the images, and then on top of the features, we do some discovery tasks, visualization or analytics tasks. So in today's talk, I will talk about how do we use deep learning to analyze electron microscopy images for the purpose of neural reconstruction, and I will also talk about how we apply these techniques for other images like optical microscopy images, and I will talk a little bit about future work as well. So as we know, there have been some workshop and tutorials on deep learning. So deep learning is basically multi-layer network where you take some raw input like image or audio signal or text input as your input, and then you have multiple layers of feature extractor to compute features at different levels, and then there is finally there will be a trainable classifiers on the top. So the fundamental idea of deep learning is different layers of this deep networks will compute different types of features. For example, the lower layers usually compute low-level features like edge and corner detectors, and high-level compute some higher-level features like object parts. And this is one of the recent breakthroughs in machine learning and in the entire area. So one type of deep learning models that have been very popularly used in image, in speech, in and other areas is convolutional networks. So convolutional network takes some structured input, structured signal as inputs, like image or video signal or speech signal as input, and it forms convolution and pooling operations. Convolution basically you apply a trainable filter on each part of the input. So in this case, it's an image, so you apply a two-dimensional convolution on each part of input. You compute another set of feature maps, and then you can also perform pooling by reducing the size of feature maps, and that will increase the tolerance to invariance of the input. So the recognition is a forward propagation process, and the training is a back propagation. Okay, and so we have been in the past probably 2 or 3 years, we have been working quite extensively on using convolutional networks coupled with other techniques, try to help neuroscientists discover the connectivity between neurons. So one of the problems we have been working on is to participate in this EM image segmentation challenge organized by a few people from MIT. So for this particular challenge, they provided a set of training images with manually generated labels. So they give you a stack of three-dimensional images, and they tell you what are the labels of each individual pixels. And they provide another test stack, which you don't know the labels, and you make predictions, and they will calculate, measure, and report that to our website. Okay. So what we have been using deep learning is, given these images, we try to use deep learning models to predict if a particular pixel belongs to the boundary of the cell or the other parts of the cell versus other parts of the cell. Because, so the motivation is although the cell is very heterogeneous, although the tissue is very heterogeneous, the borders of the cells are they are membranes, and biologically they are somehow similar, regardless of the heterogeneity of other part of the cell. So we try to distinguish the membrane of the cell versus all other part of tissue. Once we have an accurate boundary map, and by using some very simple offline in-house like MATLAB function, so you can easily fill in these interiors once you have accurate map of the boundary. So we use deep learning model to predict such a boundary map based on the input image. So this is all our flowchart. So given some EM images, the image is partition into training data and test data, and in the case of our challenge, this is already done by the challenge organizers. Then they hired some neuroscientists to manually annotate the training data, and they provide the annotations of training data and plus the test data to us. And we apply deep model, and we train a deep model on the training data to predict the boundary of if a particular pixel belongs to a boundary or not. And that model will be applied to the test data to generate a probability map of the test data. And then after we got the probability map, we use some very simple functions to generate the actual segmentation. So I will talk mainly about how to build a deep model, okay, in today's talk. So as we know, deep learning, I think, has been quite commonly used for image recognition. Basically, given an image, and the deep learning model will give you a label. For example, the well-known ImageNet challenge. So, and for our task, so our very first approach we should try is basically given an image, we need to predict a label for each pixel. So a natural way to do that is we extract a patch centered at each pixel of the input. So we get basically get a set of small patches, and there is a label for each patch. So we treat this basically as an image classification task. So you extract a set of patches from the image itself, centered on each individual pixel, and you have the corresponding labels. You feed these labels, images, patches, labels to a regular convolutional network, and it will give you a model, and you can apply that model to make predictions of each individual pixels. So this is the first approach we have been working on probably a few years ago. So there are some immediate questions here we need to ask, as Dr. Huang has been talking about deep learning. What are the parameters? So what will be the depth, what will be the size of kernels, and what is the other configurations? Should we just apply AlexNet, VGG, or any other well-known models? So we have been, so the observation we have been making is, so these commonly used models do not work for the EM images. I think there is a fundamental difference between these EM images and natural images, and our task is basically pixel labeling. We need to do pixel-wise labeling instead of image-wise labeling. So the observation, I think, is we have been making a few observations. One of them is for the size of kernels. We observed that, so in the image recognition field, basically the common practice is to apply the smallest kernel, probably a 3x3 kernel, back to back on top of each other. So, and in our case, I think what we have observed is in the lower layers, you need to use a slightly larger kernel in order to capture a larger context. And in the higher layers, probably it doesn't matter much, but it's critical for the lower layers to have larger kernels. And another observation is ensemble learning. So if you train a set of different networks, then if you do some voting scheme, you will improve performance. But the challenge with deep learning is, given this large amount of data, training even one model would take like a few weeks of time. So if you train like many models, it will take a long time for you to make training and prediction. So one technique we have been using is basically to try to simulate ensemble learning. Basically, given image patch, we randomly rotate or flip the patch by a certain degree, and we treat this as some kind of simulation of ensemble learning. Eventually, you only have one model, but this model is trained by augmented set of images, and our experiment shows this improves the performance significantly. So another key observation is this patch versus image-based prediction. So if you do the naive approach we just described, you generate a patch centered on each pixel, and you try to do patch level training and patch level prediction. So this, if you only work on a very small data set, that's still okay. But if you work on slightly larger data set, that this patch generation will almost kill all the computers, because you can imagine for each pixel you will have one training example, and even handling these patches would be a huge amount of storage and memory. So we have been working on is to do image-based training and image-based prediction only. So eventually what we can do, is during training and during prediction, you only need to give the image itself. You don't need to generate a patch. So, but the key challenge here is if you have any layer in the network that has stride, so either in the convolution or in the pooling, you have stride larger than 1. And if you give the network a larger input, it will give you a smaller output. So the size of output will be smaller than the size of input. But what we need is a prediction for each pixel. So you need an output that is exactly the same size as that of the input. But if you have any layer in between that has a kernel, that has a layer with a stride larger than 1, the size of output will be different. So you need to basically have some technique to handle this image-based prediction problem. So what has been commonly used in the field is to do some kind of staging. Basically, you shift the input by certain pixels to the right and to the bottom, and you choose. So you basically use some kind of technique to really simulate the patch-based prediction without actually generating the patch, and the result will be identical to actually you have generated patch. So you avoided that process by really understanding the very detailed how the convolution is performed. And the post-processing. So once you have the boundary map, so you just need to have some post-processing techniques to generate the actual segmentation. So in this particular two-dimensional EM images, what we used is a standard process developed by my collaborators at Utah. So they use a basic watershed algorithm to fill in these cells based on the boundary map, then build a merge tree and train a random forest classifier, predict segmentation, etc. So what we found on the 2D, this first try is this post-processing technique actually take a lot of time, because it generate all kinds of different handcraft features for the random forest, and this take a huge amount of time, and so this really become a bottleneck. So what we have been trying to do is try to eliminate this post-processing bottleneck in the following. So just give you a quick idea of how our first attempt works. So we have a total of 30 slices in the training data. We use 20 for training and 10 for validation, and we trained 4 different networks with different hyperparameters, and of course our observation is we need to have a larger kernel size in the bottom layer. Okay, so this is the very first try, and this is the 4 networks we tried initially on the 2D data set. We have A, B, C, D 4 networks. These are the configurations of each network. For example, this network takes input of a 35 by 35 patch and do some convolution, a few layers of convolution, and then do a fully connected layer. Okay, so and the challenge organizers provided 3 metrics to evaluate the result: pixel error, warping error, and rand error. And we tune our model of the training data and make prediction of the test data and submit to the challenge. So this is work we did last year, and as of June of last year, so our result of the challenge leaderboard is number 1 on 3 metrics. So this is only our first try of the 2-dimensional EM image segmentation challenge. But this first try basically lead us to some observations which motivated us to move on to further improve our method. So just a few observations from our first try. First, I think is what I already mentioned. The patch-based approach is very time-consuming, time and space-consuming, very expensive. So because once you have a large volumes, if you try to generate a patch for each pixel, centered on each pixel or voxel in 3D, then this process will already be very challenging for many computers today. So, and we try to move on to whole image-based approach. In that case, you don't need to generate a patch from the image, and you just need to give the entire three-dimensional stack to the network during both training and test. And we can show that the result of this whole image-based training and test will be identical to the result if you generated a patch during the process, but we avoided the intermediate step. So another challenge is the post-processing part. Once you have the boundary map of the neurons, and the current post-processing approaches, we have tried many, and all of them are very time-consuming because it again involves handcrafted features and build trees, random forests, etc. And this really becomes a bottleneck. So what we have been trying to do is try to improve the accuracy of the boundary map so that only a very minimal and very efficient post-processing is required in order to obtain an accurate segmentation map. Also, we observed if you try to make pixel level predictions, so you're basically trying to achieve two conflicting goals. So one is, so for example, if you have a two-dimensional image, let's say, you try to make predictions on each individual pixels, and the convolutional network usually do this convolution and pooling. So the pooling is trying to increase the receptive field of each output unit, and this will basically increase the context, increase the patch effective view field of each output unit, and that will allow you to capture one context. But on the other hand, if you do this pooling a lot, you can imagine your output size will be smaller than your input. Then you lose the pixel level accuracy. You do not make, you basically blur the image, and then it's very hard to detect a clear boundary. So you have two conflict goals. One is you try to capture larger context, because once you make a prediction on each pixel, and the label of this pixel will depend on larger context, because it's basically a cell. Okay? And on the other hand, if you try to increase the context, you will blur the image, and you will lose the clear boundary between between these two types of pixels. So what we have been trying to do is to develop a residual encoder-decoder network architecture to try to achieve these two goals simultaneously in the same model. So in that context, we have been working on a different challenge organized by the same team of people called the three-dimensional image image segmentation challenge. So the basic setup is very similar. So they provided a set of training data with labels, and they provide the test data. So you just make prediction and submit. Okay. But here the data is is a 3D data, and it's a set of slices, slices of two-dimensional images. So the whole, and the difference between the 2D and 3D basically is in the 2D you only make predictions on each individual slices. You don't need to be concerned about how the predictions on different slices are consistent. And on the 3D challenge, you have to make very consistent predictions on different slices. For example, here is a very good example. So, for example, in this particular slice, you can see this part is connected with this part through this channel, okay? But on the different slices, so these two parts are not connected, because this is really a three-dimensional thing. So some objects are connected on certain slices, but they are not connected on all slices. For example, if you only look at this particular slice, there is no way for you to label this part and this part as the same label. Okay, so you basically need to take advantage of three-dimensional information in order to make accurate predictions. You have to look at this one, say, okay, this part corresponds to this part corresponds to this part, but these two are connected on this slice. Then they must have the same label on this slice. Okay. So in the computer vision field, one popular approach that has been used for pixel-wise labeling is called this deconvolutional networks. So basically, you take an image as input, you perform some kind of convolution and pooling, etc., and you get a smaller sized feature map. Then you reverse the process. You basically do unpooling and deconvolution to reconstruct the feature map that is the same size as your input. So this is what I mean by conflicting goals. If you do a lot of max pooling, reduce the size of feature map to a very small one, and you already lose a lot of resolution information. So it's very hard for you to reconstruct and obtain a very clear boundary map because the information has been lost during this encoding process. But if you do not use pooling layers, then each output unit here will have a very small receptive field of view of the input. So you do not have a larger context information. So basically, you need to answer the question of how much information can be recovered from this small feature map. So the idea we have been developing is called residual deconvolutional network. So you have the input image, you have some convolution encoding process contains convolution and pooling. Then you have the reverse process of unpooling and deconvolution. So what we have been trying to address that problem is we add some residual connections, skip connections between the encoders and decoders directly at a various point of this network, so that this full-length network will capture the larger context, will capture the context information, and the skip connections will pass the resolution, high resolution information directly from certain encoder to certain decoder, so that you can, at this point, you can combine both the context and the resolution information into the same model, so that you can try to achieve these two conflicting goals in the same network model. So this is a key idea we developed to address this challenge in dense prediction. So in post-processing, so as we mentioned, so the post-processing step in our first attempt basically killed almost all the computers. It's a very time-consuming process. So we have been very frustrated by this process because eventually our goal is to give some images, regardless of the type, modality like EM or optical microscopy images. We want to build this automatic pipeline from end to end. Now you introduce this post-processing, you again need to do handcraft features, all kinds of traditional image features. So our basic question is it possible to minimize the post-processing process? So eventually what we were able to achieve is we really do minimal post-processing, okay? So we do not do any learning during the post-processing. We do not train any classifier. We do not extract any feature during the post-processing. Given the boundary map, what we only do is we do a kernel smoothing, okay? Basically, kernel smoothing is somehow to smooth the probability map, okay? And use a Gaussian kernel. And then use the MATLAB provided watershed segmentation really to fill in this, based on the boundary map, to fill in the inside of each individual neurons, okay? And this is very efficient. Even for images of 1,000 by 1,000, this will only take less than a minute. And compared to the previous processing will take days for images of like 1,000 by 1,000. So experimental design. So for this 3D challenge, we have a total of 100 slices for the training stack, and we used 80 for training and 20 for validation. And we compared our residual deconvolutional networks with the traditional deconvolutional networks, and this is the network trained by the agency group, which I think was on the top leaderboard on the 2D challenge, and this is the network that we tried initially. Okay, this is the network we tried on the 2D 2D challenge. So model evaluation for the 3D challenge, the organizers only use one particular measure called the rand error. So this is to measure the similarity between different segments. So it's a very customized measure they used for this particular problem of EM segmentation. And there is 100 slices of test stacks, and we do not know the label. So we submit the result to the challenge website, and the organizers computed measure to us. Okay. So visual comparison. So given this raw image, and this is the ground truth in the validation data. Okay. And these are the results generated by different methods. So for example, this is the result generated by the agency group, and this result generated by our two-dimensional model used for the two-dimensional data. This is a deconvolutional network. This is a result by residual deconvolutional network. So I highlighted a few places where apparently our method achieved better results. For example, these few boxes, the red box here, so our result is closer to the ground truth as compared to these other networks. And this is a quick comparison of the segmentation map after you applied the watershed. And this is result by the residual deconvolution network. This is the agency result, and this is the result for the 2D. Okay, so you can see visually our result-based residual deconvolution is, generate some clear boundaries as compared to other methods. You can see there's a very small over segments here, but our method generates a clear boundary. So we also try to validate how this residual idea works, how this shortcut connection helps our predictions. So for this particular test data set, so this is these are the two slices. You use traditional deconvolutional networks, and these are the results for two slices. You add these residual connections, and obviously for these larger areas you can see. So if you do not use a skip connection, so you generate a lot of over segments inside these larger segments. But if you add these skip connections, all these will be, or almost all of them will be eliminated. So validation results are the 80 versus 20 slices based on training data. So this is the rand error for different methods: residual deconvolutional network, agency deconvolutional networks, and the 2D network. So you can see the rand error for the residual deconvolutional network is much lower than any other methods as we compared. And so how this result works on the test data, we do not know. We just make predictions and submit to the website. So what eventually we were surprised is all these put together, all this entire pipeline work together, make us the first on the challenge leaderboard. And this is the current ongoing active challenge, and our result is number one. And you can see also very impressively, our result here is very close to the performance of human values. So the human value is obtained by giving the image stacks to multiple experts, neuroscientists, and they individually label all these stacks, and the error is computed by comparing the results of different neuroscientists, because they also disagree on some of the results, and you can compute the error between neuroscientists. And we can see here our result is very close to the difference between different human experts already. So there, if you cannot read the numbers, I think the human value is 0.0599, and our result is 0.060. Okay, so very close to the human values already. So that is our work on how to help neuroscientists make scientific discovery by enabling accurate segmentation and reconstruction of the neuron connectivity map based on EM images. So the next part, I will briefly talk about how to apply a similar set of techniques to our different images, like the optical microscopy images, again for the purpose of connectivity reconstruction. So for this work, we work with the Alien Institute for Brain Science, and they initiated a big project called Big Neuron, basically to try to standardize the process of reconstructing the morphology of neurons based on optical microscopy images. And what they did is they collected a huge amount of optical microscopy, light microscopy images from many different labs in the worldwide, and they collected a set of different methods to do the reconstruction. And they have a huge database of data, and they have a set of methods to perform the tracing. And this project has been highlighted in a few places, including Science and Nature. So just give you a rough idea of how the data looks. So this is one volume of the light microscopy image, and this captures the shape of one particular neuron. So you can see the light part is the body of neurons, and you have the dendrites and axons of this neuron straightened out from the neural body. We try to, given this image, we try to reconstruct the shape of each of the individual neurons. So the challenge here is this data set is quite noisy, which is true for many of the biological data sets. So, for example, this is basically we put the raw data and the ground truth onto the same three-dimensional volume. You can see this is the red part is basically the ground truth, and the white part is the raw image. So you can see we have a lot of noises from either other neurons, or we have some background noise here. So all this image. So we have been trying to help them is we try to develop a deep learning-based denoising method to remove the noise. So there have been some previous attempts to do the tracing reconstruction. So these are the references of prior work. We did not try to make a new tracing method, but try to using deep learning method to denoise and to remove the noise of the data, so that any other tracing method can be applied downstream. So our proposed method is pretty simple. So you give the image, we generate a probability map that each individual voxel belongs to the neural body or not. And then based on our prediction, we use this probability map to adjust the original image. And in that way, we try to remove the noisy pixels from the image, and then we apply any kind of downstream tracing method. Okay, so probably I will skip these details of model we try to use. We use the idea of inception learning coupled with the idea of residual learning in the same network, and here is our model. So we have input, and this is our output. We have an entire process of many modules. Each module is a combination of inception coupled with the idea of residual. So this entire network is roughly about 200 layers in total, from the input to the output, trained end to end. Okay. Here is a quick result comparison. So this is two different volumes, and this is the manual reconstruction ground truth, and this is our prediction. And these are the predictions by two other prior methods. So you can see our result is closer to the ground truth than these two methods visually, and we also compared quantitatively. And so these are each different data sets. Each row corresponds to a data set, and these three blocks correspond to three different measures, different metrics to quantify the accuracy. And these are so our method basically is the denoising method. If our method is coupled with APP2, you can see it improves upon APP2. If you look at this column with this column, so if you apply denoising, the tracing accuracy is improved consistently, and this is true for across different three metrics as well. Okay. So Pretty much that's all my talk. So, to conclude, I talk about method for deep learning method for analyzing EM and light microscopic images, and we have been doing some open challenges. We are top performers, and in particular for the 3D challenge, our performance is very close to the human level performance as well. So currently, we are still working on improving our method. So we try to incorporate really the topological structure of the boundaries into the prediction process. Currently, we only increased the receptive field size, but we did not explicitly consider the fact that the boundary really follow certain topological structure, and we will so also. The segmentation step is only one of the steps during the reconstruction. So we will try to extend our method to other steps like synapse detection and other steps. And so a key also will be how to enable large-scale analysis. So we currently work on images of 1,000 by 1,000 by 1,000. So eventually, my collaborator told me they will have the EM image for the entire mouse brain within the next 5 years. So they will have a huge amount of data, EM images, to capture the entire mouse brain in the next 5 years. So how to enable large-scale analysis, how to scale our method to really huge data set would be a challenge for us to work on. So finally, I want to thank all my students who have been working very hard on this data set. Particularly, Ahmed has been working on the 2D challenge, and Rongjie has been working on the light microscopy associated with big neuron, and Tao has been working on the 3D challenge. And my collaborators, Han Chuanpeng from Allen Institute, and I also work with Sebastian from Princeton, working on the 2D and the 3-dimensional reconstruction, and Toga from Utah also provided us the post-processing for the 2D challenge. And I'm very grateful to National Science Foundation for their support of my research. And thank you very much for your attention.